So you're outside and you're bored. Wait, that's not really completely safe yet. So you're inside and you're bored. And you have your handy dandy ruler 12 inches long. But whoops, you drop it on the floor and it lands while touching a tape line that was there earlier. And you look around and you find a bunch of tape lines on the floor that are each a foot apart. Huh, how convenient. And you look at the fact that the ruler landed on the tape line and you ask, golly gee, what are the odds? That's a good question. Let's work it out. So, for the sake of argument, let's imagine that the ruler is 2 units long instead of just 1 unit long or just 1 foot long. This will come in handy later. Now, if we drop the ruler and say it lands parallel to the lines, that's basically never going to touch the line unless the ruler is right on top of the line. If the ruler drops and is perpendicular to the tape lines, then it's always going to touch a line unless the midpoint of the ruler is exactly between the two lines, which is really unlikely. But a ruler doesn't just fall parallel and perpendicular to lines. It can fall in 45-degree angles, 75-degree angles, and any which angle. So how do we account for that? Well, our old friend from high school, who you only had 2 classes with, is going to help us a lot. Trigonometry. Let's make this easier on ourselves and work on some paper now. Now, let's be more specific on what we mean by crossing a line. To accomplish that, we have to define some variables. Everyone's favorite part. As with any mathematical problem, defining variables often makes the numbers in the question easier to deal with. For that reason, let's define h as the distance between the center of the ruler in question and the nearest tape line. Now, obviously, h can't be bigger than 1, as the greatest distance from the center of the ruler can be from any particular line is 1. Because as it gets farther away from one line, it gets closer and closer to another tape line. This is because the distance between each line is 2 units or 1 foot. And our second variable will be theta, the angle at which the ruler sits in respect to the lines. Well, now that we have 2 variables, what has to be true about these values when the ruler crosses a line? Well, if you look at the ruler closely and draw a really strategic right triangle at here, you can actually see that the sine of theta can show how close the ruler is to touch it. As you can see, if the sine of theta is greater than the distance between the ruler and the line, also known as h, the lines will cross. Well, now we have 2 variables, and we can use that to map our problem onto a graph. Let's imagine that our x-axis is all possible thetas, from 0 to pi. It's only 0 to pi because if we went past pi, then we would just be repeating previous arrangements. And our y-axis is h, the distance between the center of the ruler and the line. Those distances, as we explored earlier, go from 0 to 1. Every point in this graph is a different possibility of how the ruler could fall on the line. For example, a point here could say, oh, we're at pi over 3 radians and we are 0.5 units from the line. What we want to find out is what portion of this graph results in arrangements of the ruler where the ruler is touching a tape line. We want to find the portion of possibilities, or as people put it, a probability. Now, remember that the sine of theta has to be greater than h, the distance between the center of the ruler and the nearest tape line. So, if we graph sine of theta, we'll find that the area that we're interested in lies under the curve, as this is the area where sine of theta is literally greater than h. Now, we need to find the portion of the full area this curvy area takes up. If you know some integral calculus, that's a pretty simple problem to solve. So, we can find the area of the sine curve and divide it by the full area, which is very clearly just pi. The area under the curve is also pretty trivial, as you could find out is just 2. Now, dividing that by pi, the full area, we get a probability of 2 over pi. which means that if we picked a random point in this graph, the probability that it would land under the sine curve would be 2 over pi. Or, more accurately to our original problem, if we drop the ruler, which would result in a random angle and distance from the closest tape line, we would expect it to have a chance of 2 over pi of it hitting a line. Fun! This problem is called Buffon's needle. And the guy who invented it essentially saw this and thought, wow, if I drop a lot of needles, or rulers in our case, I can find out what pi is experimentally. So say you dropped a lot of rulers, and we know how many hit a line, and you obviously know how many rulers you dropped in total. And according to our calculations, the proportion of rulers that touch the line compared to total rulers is 2 over pi. So if we take the proportion that we got experimentally and compare it to the theoretical solution, getting pi isn't that hard. You should really try it if you're bored, inside, and have random tape lines on your floor, as of course, we all do. Thanks so much for watching. This isn't going to be the last time we tackle a problem like this, where we're dealing with probabilities of things that are very continuous in nature. I hope you'll stick around till then. Again, thank you so much for watching, and if you like this video, please consider liking or subscribing. See you next time.